Could an entire mountain range be hiding enough water to rival some of the largest reservoirs in the United States? How could billions upon billions of gallons remain concealed beneath volcanic rock for thousands of years, while rivers, lakes, and snowfields above gave only hints of what lay underneath? And why are scientists now warning that this enormous underground reserve may completely reshape how the American West understands water security, volcanic hazards, and the future of life in the Cascades? Deep beneath the towering volcanic peaks of Oregon's Cascade Range, researchers have uncovered evidence of an underground aquifer so vast that it has stunned hydrologists and geologists alike. Hidden beneath layers of fractured lava rock, porous volcanic deposits, ancient flows of basalt, and snow-fed mountain terrain lies an immense body of groundwater stretching across the crest of the central Oregon Cascades. The discovery has transformed scientific understanding of how water moves through the Pacific Northwest, and revealed that the mountains themselves function as an enormous natural storage system. The newly mapped aquifer is estimated to contain at least 81 cubic kilometers of water, equivalent to roughly 19,400 cubic miles or more than 21 trillion gallons. That amount is nearly 3 times the maximum storage capacity of Lake Mead, the giant reservoir along the Colorado River that supplies water to millions across the American Southwest. Researchers also determined that the estimate likely represents only the lower boundary of the aquifer's actual size, because many sections of the mountain system remain poorly sampled. Despite sensational descriptions circulating online about a massive underground ocean, the reality is even more scientifically fascinating. This is not a giant cavern filled with free-flowing water like a hidden subterranean sea. Instead, the water is stored throughout networks of cracks, pores, and fractures inside volcanic rock that accumulated over millions of years of eruptions across the Cascades. The mountains effectively act like an enormous sponge made of lava and stone, continuously absorbing snowmelt and rainfall before slowly releasing water into rivers, springs, and streams across Oregon. The scale of the discovery became clear after researchers examined temperature records from deep boreholes drilled decades earlier during geothermal exploration projects. During the 1980s and 1990s, scientists searching for geothermal energy sources drilled extensively into parts of the Cascades to study underground heat. Those boreholes were never intended to reveal a hidden water reserve, yet they eventually provided the crucial clues. Ordinarily, temperatures increase steadily with depth inside Earth's crust. However, in many drill holes beneath the Oregon Cascades, temperatures remained unexpectedly cool far deeper underground than expected. Scientists realized that groundwater moving downward through volcanic rock was carrying surface temperatures deep into the subsurface, disrupting the normal geothermal gradient. By studying how deeply this cooling effect extended, researchers could estimate how far groundwater penetrated underground and how much water the volcanic formations were capable of storing. The Cascades are uniquely suited for such a system because they are among the youngest volcanic mountain chains in North America. Stretching approximately 700 miles, or 1,127 kilometers from Northern California into British Columbia. The range was built through repeated volcanic eruptions associated with the subduction of the Juan de Fuca tectonic plate beneath North America. Over immense spans of geological time, lava flows stacked upon one another, creating thick formations filled with cracks, cavities, and broken rock layers capable of trapping water. In Oregon's high Cascades, volcanic rocks are relatively young and highly permeable. Water from melting snow and seasonal rainfall seeps downward rapidly through the fractured terrain rather than remaining on the surface. Unlike older mountain systems where solid crystalline rock blocks deep infiltration, the volcanic geology of the Cascades allows water to descend hundreds and sometimes thousands of feet underground. The mountains effectively function as giant recharge zones. Every winter, heavy snowfall blankets the peaks and volcanic plateaus. During warmer months, snow melt slowly percolates through lava fields and porous rock layers. Instead of immediately rushing downhill, much of the water disappears underground into hidden aquifers, before eventually re-emerging through springs and rivers farther downslope. This process explains why many rivers in Oregon maintain remarkably steady flow rates even during dry summer periods. Water released gradually from underground storage continues feeding streams long after seasonal snowpack has melted away. Rivers such as the Mackenzie owe much of their stability to this hidden hydrological system beneath the mountains. The discovery also reveals how incomplete previous water estimates for the Cascades may have been. Earlier calculations focused primarily on visible surface water, including lakes, rivers, snowpack, and stream discharge measurements. Those methods failed to fully account for the enormous volume stored underground within volcanic rock formations. Researchers now believe the Cascade Range may contain one of the largest volcanic aquifer systems on Earth. Similar geological conditions extend northward into Washington and southward toward Northern California near Mount Shasta. If comparable underground reservoirs exist throughout the broader Cascade system, the total amount of groundwater hidden beneath the mountains could be extraordinary. The implications extend far beyond Oregon itself. Water security has become one of the defining challenges facing the western United States. Climate change has intensified droughts, reduced snowpack, increased evaporation, and placed enormous stress on reservoirs across the region. The Colorado River Basin, which supports tens of millions of people, has experienced severe shortages during prolonged dry periods. Reservoirs, including Lake Mead and Lake Powell, have reached historically low levels in recent years. Against that backdrop, the discovery of a massive underground water reserve in the Pacific Northwest immediately drew national attention. The Cascades already supply much of Oregon's drinking water, irrigation resources, hydroelectric generation, and ecological support systems. Understanding how much water is actually stored underground could significantly alter long-term planning for cities, agriculture, and environmental management throughout the region. Yet the findings also came with major warnings. The aquifer is not an unlimited supply immune to climate change. In fact, its long-term stability depends heavily on consistent recharge from mountain snowpack. Researchers emphasized that the system functions because snowfall accumulates during winter and melts gradually across spring and summer. If warming temperatures continue reducing snow accumulation, the recharge process may weaken. Climate projections for the Pacific Northwest indicate that more winter precipitation may increasingly fall as rain rather than snow. That shift could fundamentally alter how water enters the aquifer. Snowpack acts as a slow-release storage mechanism, feeding groundwater steadily over time. Rainfall, by contrast, often runs off more quickly and may not infiltrate as effectively into volcanic formations. A prolonged series of dry winters or diminished snow seasons could eventually reduce groundwater replenishment. Even a gigantic aquifer can decline if recharge consistently falls below discharge. The discovery therefore highlights both the abundance and vulnerability of the region's water system simultaneously. The underground reservoir also carries important implications for volcanic hazards in the Cascades. Water and magma form a particularly volatile combination inside volcanic systems. When magma rises and encounters large quantities of groundwater, intense heating can generate enormous steam pressure. That process often produces explosive eruptions capable of blasting ash, rock, and gas high into the atmosphere. The Cascade Range contains numerous active and potentially active volcanoes, including Mount Hood, Mount Jefferson, the Three Sisters Volcanic Complex, Newberry Volcano, and Mount Shasta, farther south. The discovery that large volumes of groundwater exist within volcanic formations means scientists must consider how underground water interacts with magma chambers and volcanic conduits beneath the mountains. Past eruptions throughout the Cascades have demonstrated the destructive potential of water-driven volcanic activity. Steam explosions can fragment magma violently, producing ash-rich eruptions far more explosive than relatively gentle lava flows. The presence of widespread groundwater systems may therefore influence future volcanic behavior in ways not previously understood. The geological architecture responsible for the aquifer developed over millions of years of volcanic construction. Each eruption contributed additional layers of lava, ash, pumice, and fragmented rock. Some flows cooled into dense basalt, while others solidified into highly vesicular formations riddled with gas bubbles and open spaces. Faults, fractures, and cooling cracks further increased permeability. Over time, glaciers, rivers, and erosion sculpted the landscape while groundwater continued infiltrating deeper into the volcanic pile. The result is an intricate three-dimensional network where water moves through interconnected pathways beneath the mountains. In some locations, groundwater likely travels considerable distances underground before resurfacing. Springs emerging at lower elevations may contain water that entered the subsurface years or even decades earlier high in the mountains. This hidden circulation system plays a major role in regulating temperatures, sustaining ecosystems, and maintaining stream flow during drought conditions. The discovery also demonstrates the extraordinary value of revisiting older scientific data with new perspectives. The geothermal drill holes that enabled the aquifer mapping were originally created for entirely different purposes. Decades later, researchers realized that temperature measurements collected during those projects contained overlooked evidence of extensive groundwater movement. By integrating geothermal data with hydrology, volcanology, and geological mapping, scientists were able to reconstruct the underground structure of the aquifer with far greater precision than previously possible. The work highlights how major discoveries sometimes emerge not from entirely new expeditions, but from recognizing hidden patterns within existing information. The aquifer beneath Oregon also challenges popular assumptions about where fresh water exists on Earth. Surface lakes and rivers are highly visible, yet much of the planet's fresh water resides underground. Aquifers supply drinking water to billions globally and support agriculture across entire continents. In volcanic regions especially, groundwater systems can become enormous because fractured rock provides abundant storage capacity. Still, the Oregon discovery stands out because of both its scale and location. Few expected that such an immense groundwater reservoir existed beneath one of North America's most prominent mountain chains. The findings suggest that volcanic landscapes elsewhere may also conceal vast underground water systems awaiting detailed mapping. Communities throughout Oregon have long depended on water originating in the Cascades, even without fully understanding the hidden infrastructure beneath the mountains. The Mackenzie River supplies drinking water to Eugene. Countless smaller streams support fisheries, farming, forests, recreation, and hydroelectric systems. Springs emerging from volcanic terrain sustain ecosystems even during dry periods. Now researchers recognize that many of those surface waters are expressions of a much larger subterranean network. Rivers visible on maps represent only part of the hydrological system. Beneath them lies an immense reservoir continuously exchanging water between snowpack, groundwater, springs, and streams. The discovery arrives at a time when water politics across the western United States have become increasingly contentious. Interstate disputes over river allocations, declining reservoirs, groundwater depletion, and agricultural demands have intensified under persistent drought conditions. Knowledge of previously underestimated aquifers could influence future planning decisions involving conservation, land use, forestry, and regional development. At the same time, scientists caution against interpreting the discovery as a limitless new resource available for unrestricted extraction. Aquifers are dynamic systems. Excessive pumping can lower groundwater levels, reduce spring flows, damage ecosystems, and alter river systems. Sustainable management requires understanding recharge rates, flow pathways, and long-term climatic influences. The volcanic nature of the aquifer introduces additional complexity. Water moves differently through fractured lava than through traditional sedimentary aquifers composed of sand and gravel. Flow pathways may shift over time due to earthquakes, volcanic activity, mineral deposition, or changing recharge conditions. Mapping such systems remains extremely challenging. Researchers also stress that the estimated 81 cubic kilometers likely understates the true volume. Borehole coverage remains incomplete across large portions of the Cascades. Some volcanic formations have never been sampled in sufficient detail. Future drilling and geophysical surveys may reveal even larger connected groundwater systems extending farther beneath the mountains. Public fascination with the discovery has been fueled partly by descriptions comparing the aquifer to an underground ocean. While scientifically imprecise, the phrase captures the sheer magnitude of the water involved. 21 trillion gallons represents an almost unimaginable quantity. If spread across the landscape, it would cover enormous areas in water hundreds of feet deep. Yet unlike an open underground sea, the aquifer exists as water occupying countless microscopic and macroscopic spaces inside rock formations. Some water fills tiny pores between mineral grains. Other portions move through fractures, lava tubes, and broken volcanic layers. The system is diffuse, complex, and constantly in motion. The findings also reinforce the profound relationship between mountains and water resources. Mountain ranges function as natural water towers for much of the world. Snow accumulation, rainfall capture, and groundwater recharge occurring at high elevations ultimately support downstream populations far beyond the mountains themselves. In the Cascades, volcanic geology amplifies that role dramatically. Instead of merely shedding snowmelt downslope, the mountains absorb and store water internally, releasing it gradually over time. This underground buffering system may help explain why parts of Oregon maintain relatively resilient stream flows even during seasonal dry periods. However, resilience has limits. Climate models suggest warming temperatures could significantly reduce Cascade snowpack during coming decades. Higher freezing levels mean storms increasingly deliver rain at elevations that historically receive snow. Earlier snowmelt may shorten the duration of summer stream flow. Wildfires, which have intensified across the West, can further alter hydrology by changing vegetation, soil stability, and infiltration patterns. All those changes could influence the aquifer's future behavior. Scientists are now focusing on critical questions involving recharge rates, groundwater age, seasonal storage fluctuations, and long-term sustainability under changing climate conditions. The newly identified water reserve may become one of the most important hydrological research targets in North America. The discovery also highlights the hidden complexity beneath seemingly familiar landscapes. Millions of people have traveled through Oregon's Cascades for generations, seeing snow-covered peaks, lava fields, alpine lakes, and dense forests without realizing that an enormous groundwater reservoir lay beneath their feet. The mountains visible above ground represent only part of the geological system. Below the surface exists another landscape entirely, shaped by fractures, buried lava flows, water pathways, and immense underground storage zones. Modern technology and interdisciplinary research are increasingly revealing such concealed structures around the world. Advances in geophysics, satellite observations, thermal imaging, seismic analysis, and groundwater modeling allow scientists to peer into Earth's subsurface with unprecedented detail. Aquifers once poorly understood can now be mapped across vast regions. Even so, the Oregon discovery demonstrates how much remains unknown about groundwater systems globally. Hidden water reserves may influence ecosystems, climate resilience, volcanic hazards, and human survival in ways still poorly understood. Beneath many mountain ranges, deserts, coastal plains, and volcanic regions lie underground systems far larger and more interconnected than surface observations alone would suggest. In Oregon's case, the Cascades have effectively been storing water for geological ages, quietly functioning as a massive natural reservoir hidden inside volcanic rock. Snow falling on the peaks each winter begins a journey through lava, fractures, and underground channels that may continue for years before the water finally emerges downstream through springs and rivers. The realization that such a colossal reserve exists beneath the mountains fundamentally changes how the region is viewed. The Cascades are no longer simply a chain of volcanoes and forests rising above the Pacific Northwest. They are also one of the continent's great hidden water systems, a buried reservoir built by fire, sustained by snow, and concealed within stone. As researchers continue probing deeper into the volcanic heart of the mountains, the full dimensions of the aquifer may become even more extraordinary. Additional surveys could reveal broader connections across the Cascade Arc, uncover older groundwater systems, or reshape understanding of how volcanic terrains store and transport fresh water. For now, the discovery stands as one of the most significant groundwater findings in recent American geological research. Beneath Oregon's iconic peaks lies a hidden reservoir vast enough to rival major surface lakes, yet invisible to anyone standing above it. The mountains themselves have been guarding one of the Pacific Northwest's greatest natural resources all along.